All right, guys, we're going to talk about ionic equations, and I'm going to pay close attention to something of sort of writing net ionic equations. Now, this is going to expand your knowledge of ionic reactions, and so part of it deals with your ability to identify solubility rules. So hopefully you've built up a repertoire of understanding whether something remains a solid, forms a solid, which means to kind of crash out a solution and form a precipitate, or if a solution or substance is perhaps soluble in that water aqueous media, then you know that it can actually be broken down into its respective ions. So for instance, when we talk about our most common compound, NaCl. NaCl is table salt, sodium chloride. When suspended in the water, this is what that looks like. Now, they are still together. There's an electrostatic interaction, but we represent how they behave in solution in this manner. Now, part of that stems from the solubility rules. If you recall, there's a list of rules that talks about certain solubilities, like all salts of group 1A and ammonium are soluble, salts of nitrates, chlorates, and acetates are soluble. Salts of halides are soluble except those with silver, copper, lead, and mercury. Those kind of list of rules. And that list is an invaluable technique that you're going to need going into this unit. Now, fortunately, when we're talking about ionic equations, or in this case, net ionic equations, the good news is that you don't have to have any math. This is just body of knowledge trying to recognize the rules of solubility and using that to write a net equation. And so, a little bit here. So when we write it, we're going to have to know our states of matter, and we have to consider what will form a precipitate. So let's go ahead and look at just one model setup, shall we? Let's look at the reaction between lead nitrate, which is aqueous because it's soluble in solution, and potassium iodide. Now, these two compounds form a binary product. The binary product means that they're going through an exchange. The cation switch with a new anion partner, so to speak. And so you end up forming lead iodide plus potassium nitrate. Now, here's where the solubility rules are most important. You need to know that these two are aqueous in solution. Now, when they form a product, that product is going to be a solid. We have a solid here, and that's aqueous. Now, the reason we know this is a solid comes from solubility guidelines. Solubility guidelines. And you need to know those solubility guidelines, which is why you would benefit from reviewing those rules if you're not familiar with them. Now, knowing that information, we're now going to break it down into what's called its net complete ionic equation, where we're looking at how it breaks down if it's soluble, and if it's not soluble, how they tend to stay together in solution. So rewritten, this would look like this. Pb2 plus, or plus 2, however you want to put that, aqueous, plus NO3, which I didn't balance it, the other one. I'll go ahead and balance the initial equation. There's a 2 goes there and a 2 goes here, and that's balanced. Sorry. So now that's balanced. Then you have your NO3 minus AQ. Remember, there's 2 of those guys coming from this 2 here. Coming from that 2, this is 2 here. That's where that 2 comes from. Plus 2 of the K's plus iodine. There's 2 of those as well. That's aqueous. And the product from that yields is this. Remember, this is solid once they fuse together. So this doesn't actually break up in solution. It remains this stiff lead iodide precipitate that's insoluble in water. So it doesn't form its respective ions. And so those fuse together. But then you have this guy here from the potassium nitrate. And you also have this guy here, which is the nitrate group. And we know those are soluble because we kind of know the states of matter. Aqueous, aqueous, soluble, aqueous. Now sometimes these states of matter aren't given, so it's hard to tell what forms, but if you know that it's forming a solid, 9 times out of 10 you're going to use that to kind of elicit your solubility and use that to deduce your net ionic equation. Now this is our complete ionic equation. We're looking for a net ionic equation. Now to get a net ionic equation, you have to remove something called the spectator ions. So we're remove the spectator ions. Now, for a spectator ion, they're basically ions that kind of are part of the equation, but they're there on both sides, and they're almost null and void, so to speak. So they appear in identical forms on both the reactant and product side, and so they're not playing any direct role in the reaction. They're not like chiefly responsible for the formation of the product. And so when you look at identifying spectator ions, you want to find an ion that's common on both the reactant side and the product side. So in this case, if I'm going through, I'm looking at my spectator ions, I'm going to look at nitrate being over here, and there's a nitrate over here. And I'm going to draw a cross through it. Then I'm going to look and see if there are any other ions where I'm finding them on both the reactant and the product side. And conveniently, I see that that's that, and that's that. Now, once I've done that, I've eliminated all the ions that are found both on the left and the right. And if you look at the left and right comparison between the reactant and the product, this is lead ion here and this is iodide ion here. But on this side, you have this lead iodide solid product that doesn't form any type of soluble ions. And that's part of its insolubility rules. And the only reason you know to predict to write this like this is because this remains a solid. This is solid. And you know this is solid if you know the solubility guidelines. So it becomes hugely important that you know your solubility rules when identifying your ion equations. So knowing that, let's go ahead and look at a couple of them and just get a little bit more practice under our belt. And so we'll start here with just a very common reaction. We have silver nitrate. And we're going to react that with KCl, which is potassium chloride, and that's going to yield silver chloride plus potassium nitrate. Again, we have binary compounds, 2 binary compounds reacting. You know that's going to be a double replacement reaction, and we need to know our solubility rules to know if it produces a solid or remains aqueous in solution. I can tell you right now, silver nitrate is AQ. I can tell you KCl is also AQ. Now, when they react, silver chloride, a very infamous precipitate, forms. And then potassium nitrate, which we've seen in the previous question. Now, if I'm writing my ionic equation, I'm writing it like this. I know that Ag plus, matter of fact, let me make sure it's balanced again. Ag, Cl, looks balanced to me, so let's go ahead and move forward. Ag plus, there's one of those. There's NO3 minus plus K plus Cl yields AgCl. That's a solid, so it doesn't become an ion in solution. Plus K plus NO3 minus. Now, if I'm looking to eliminate my spectator ions, I'm looking for comparable ions that are found on both the reactant side and the product side. So if I look on my left and I scan how that compares with my right, the silver remains intact here, so that's not a free spectator. My nitrate, however, if I look at the nitrate here and I look at the nitrate here, both of those are ions, so I'm going to just cross those out like that. And then scanning, I see potassium and potassium here. And I see a chlorine here, but I notice that it's fused with the silver chloride there. So therefore, I'm going to rewrite it as such. Ag plus Cl minus yields AgCl. And for all intents and purposes, if I'm including my states of matter, this is AQ, this is AQ, and that's solid. So it's as simple as that when you're writing those net ionic equations. Now we're going to look at one more just to kind of make sure that we have that additional practice. And again, it is going to be very invaluable that we know our solubility rules. So if we don't know our solubility rules, we will need to revisit those rules. So let's look at one here where we have this guy, which is potassium phosphate, AQ, plus aluminum nitrate. Now, those both are soluble in solution. They're both soluble in solution. And if we're looking at their ability to form a product, we again are going to feature double replacement. Double replacement means that our products are going to be as follows. For this reaction, we will yield aluminum phosphate, and we will have potassium nitrate. And because I like having things balanced, I'm going to go ahead and balance it. I'll put a 3 in front of my potassium nitrate, then that should fix everything. Now, what I like to do now is focus on the products and their solubility. For me, aluminum phosphate remains a solid. Potassium nitrate forms aqueous. Now, interestingly enough, even though I wrote it this way, sometimes your solid can be on this side. It doesn't matter. It just really depends on what's soluble and what's not. So when I begin to write my complete ionic equation, I'm going to write it with everything being ionic except this solid precipitate that is formed. So I have my potassium, which I have 3 of those guys, by the way. I'm going to add that to my phosphate group. Then I'm going to add my aluminum. Then I'm going to add my nitrate, which there are 3 of those guys. And that's going to form aluminum phosphate, which remains a solid, so it doesn't form an ion in solution. I'll put that solid in there to kind of indicate that. Plus my 3 potassiums, plus my 3 nitrate groups. Now, when I begin to remove my spectators, we're looking only for the ions that are free-flowing in solution and haven't formed some insoluble product on one of the sides. So we have potassium and potassium, so we can eliminate those as spectators. Phosphate is an ion here, but it's not an ion there, so phosphate's intact. Next, we have aluminum. That remains intact as well. If we look at nitrate, this nitrate and this nitrate are both ions, so those are spectators. Rewritten, I'd probably rearrange my order, but I'd write it like this: Al3 plus, PO4, 3 minus, yields AlPO4 solid. And that, my friends, is my net ionic equation. So the process is relatively simple. It just comes back to being able to diagnose the products and the solubility rules. And whenever we're dealing with these reactions, a lot of these are going to be binary compounds. Now, there may be some episodes where everything remains soluble or everything remains a spectator ion in solution. When that happens, it's okay to put no reaction for the net ionic equation, because if everything is soluble, then there is no net ionic equation. That means everything is just free-flowing in solution. So hopefully we've covered that, and thank you for tuning in.